Hey guys, welcome back to another video. In this video, we're going to talk about circular orbits in a gravitational field. That is, we know the moon is orbiting around the Earth. But why is it orbiting? How is it orbiting? And at what speed or at what rate is moon orbiting around the Earth? How can we calculate all those figures? So to do that, we're going to understand a bunch of things. First of all, we're going to recall that the force between two masses is going to be the exact same. So let's say M1 is going to exert force Fg on M2. M2 is also going to exert the same force Mg on M1. So the force is actually equal. Now, notice one thing. In case of circular motion, if you've already studied that topic, what is necessary for an object to be in circular motion or in a circular orbit is there needs to be a force that is perpendicular to your velocity of the object. So let's say an object is at this instantaneous point is moving in this direction. There needs to be a force that is perpendicular to it. Now, when the mass moves over here and has a velocity in this direction, your force still needs to be towards the center and perpendicular to your velocity. So these few things need to be considered when you have circular motion or circular orbits in case of planets. So what's happening in our case is we have a moon orbiting around the Earth. Now, this force that is between both masses is going to contribute towards their centripetal force. That is, the force perpendicular to the mass's velocity. Therefore, the gravitational force is actually providing the centripetal force. Now, we know the formula for what centripetal force is. That is, we know Fc, centripetal force, is equal to mr omega squared. So we know the formula for Fc, that is centripetal force. We also know the formula from the previous video, that is of the gravitational field, force due to an object's gravitational field. So we know both of these formulas. Now, from these two formulas, can we figure out anything about the orbit of moon or any planet or any star around, not star, but any object, any mass around the Earth? Yes, we can. So if we equate both of these equations, that is Fc is equals to mr omega square, that is the centripetal force, and you know the force due to the gravitational field, G m, the product of mass divided by their separation square. So here is the Fg. We also know the circular motion's centripetal force. So we can equate both of these together, that is mr omega squared. M is the mass of the object that is orbiting. In our case, if you consider this to be the moon, the mass of the moon. So mr omega square, mass of moon, times the separation between the center of both the objects, and omega square is the angular velocity or angular frequency of the moon. At what rate is the moon revolving around the Earth? Right. And gmmr square, G is a constant, mass of Earth is a constant, we know it, and mass of the moon is actually going to be cancelled off from either sides of the equation. And you have again the separation squared. So what you can do over here is you can make r cube the subject, that is this r is going to go over here and it's going to give you r cube times this omega. You can break down as 2 pi by t, because you know omega is 2 pi by t, right? This is your formula for angular frequency from circular motion. You can also write it as omega is 2 pi f, but this is not going to help us over here. So we can write omega as 2 pi by t whole squared is equals to gm. Now what you can do over here is you can take everything on the other side, leave the r cube, and what you're going to have is gm times t square divided by 4 pi square. Now what this gives us is an interesting proportionality. That is, r cube is proportional to t square. What this means is the cube of their separation is proportional to the time period, proportional to the square of their time period. So this is actually Kepler's third law, but you don't need to understand Kepler's first and second law. Only Kepler's third law is going to be useful to you in this syllabus. Now, what this tells us about the orbit is if you increase the separation, your time period of the orbit is also going to increase. Therefore, if Moon had a greater separation away from Earth, it would have a greater time period. And you can also say the opposite thing. So if it had a lower time period or a smaller time period, its radius would have to be smaller, right? So that's what we can understand from this proportionality. Now, that is what we understood from equating both the forces together. Now, let's say you want to understand at what speed is Moon revolving around Earth. What is its velocity, right? In that case, what you're going to do is you're going to use another formula for centripetal force. Even in this case, notice the centripetal force is going to be given by your gravitational force. So your centripetal force you can write as mv squared, because you want to find the velocity of the Moon. So mv squared by r, right? mv squared by r is your centripetal force, and your gravitational force is going to be gmm by r squared. So this is your centripetal force, and this is your force due to gravitational field. Now both of these are equal because gravitational field is actually providing the centripetal force, right? So if you equate both of these together, what you're going to see is if you make velocity the subject, you're going to have v squared over here, v squared, and you're going to cancel off one of the r's. So you're going to be left with, oh, by the way, you're also going to cancel the mass of the Moon, right? So you're going to be left with the gravitational constant times the mass of Earth, and that is going to be equal to the square of velocity. So now if you want to make just the velocity the subject, you're going to have gm by r. So what we now understand is if you want to find the velocity of the Moon, you have to know the gravitational constant, which you already know, the mass of Earth, which you might know if you just search, and the radius, that is the separation from the Earth's center to the Moon's center. If you know that separation, you can find the velocity at which the Moon is traveling. Now, there is something interesting about this formula. If you have noticed, in this formula of velocity of the Moon, the mass of Moon is not mentioned. So what this tells us is it doesn't matter how heavy or how large the mass of Moon is, it is going to have the same velocity at the same distance away from Earth. So even if, let's say, Moon was 10 kgs or Moon was 1,000 kgs, it wouldn't affect its tangential velocity. It wouldn't affect its velocity at which it is revolving around the Earth. So its mass is not a factor, which is why the radius is actually going to determine at what pace, at what velocity Moon is going to revolve, right? So your radius is the only factor because mass of Earth is not going to change, gravitational constant is not going to change either. So your radius is going to be the factor over here. So different objects at different separation away from Earth is going to have a different velocity. Granted, the gravitational field is providing the centripetal force. Okay, so up till now, we understood Kepler's third law, the proportionality of radius, that is separation and time period. We also understood how to find the speed of any planet, any object that is orbiting around Earth. And we understood that mass is not a factor over there. The radius is going to determine at what pace, at what velocity an object is going to move around. So for this video, that is going to be it. And in the next video, I'm going to cover geostationary orbits. That is how satellites are able to stay where they are without falling towards the surface of the Earth or towards the center of the Earth. Why is it that they're able to maintain their fixed position above Earth? And how do we find their orbit? And how do we find at what distance, at what altitude do they need to be to maintain their orbit? So we're going to see that, understand about that in the next video.